We can use the linear regression for nonlinear data as well. We can have some conversion of the data, then use it for the linear regression. Simply, if we have a nonlinear data, we have two options. First, a transformation to a linear relationship can be done, then a linear regression can be used. And also, linear regression may be never appropriate. So then we need a polynomial regression. If you cannot transform it to a linear relation, then you need to fit a polynomial regression. A higher order polynomial fit is required with the least squares again. So for the nonlinear relationship, always first check if a linear transformation is possible or not. You can see this is basically a nonlinear data. If we apply a linear regression directly to this, it is not suitable actually. We need to check if we can make the data somehow transform it to a linear version. If not possible, then use a higher order term, a higher order polynomial to be able to have a good regression like this. When we have a data which shows a nonlinear linear relationship, we can first think of whether we can convert it to a linear relationship. So for example, we have three options first of all for this in this class. Exponential model, so we can have a data which shows an exponential relation, and the function can be like this. When you fit this function, it will fit very well to the data. But what we want to do is we don't want to go with this complicated function. We simply use the linear regression. For that, we need to transform this to a linear data, you can see, and we can achieve that using ln, the natural algorithm actually. Take the ln of these values and also x values here, and the function will be like this, a linear regression function, ln y equals ln a alpha 1 plus beta 1 x, and these alpha and beta actually are the coefficients of this exponential function alpha 1 beta 1. So if you take ln of both sides, it will give this linear function to us. Then you can apply the regression, linear regression with least squares and get this value and beta 1 value, and from there you can obtain alpha 1 and beta 1. Then you can convert it to this function as well. So the intercept here is ln alpha 1 and the slope is beta 1 for a natural algorithm converted data, which is linear. The second option is a power equation. Its increase, nonlinear increase, can be less than the exponential increase like this. Then it will have a non-power equation like it is similar, actually alpha 2, alpha 1. But here instead of epsilon, or sorry, exponential, we have directly the x, beta 2. So here beta 1 x is at the top. It's the difference. We can convert this to a line as well using base 10 logarithm. So here natural logarithm ln, here base 10 logarithm. When you use base 10 logarithm for this function, you can simply have this function. It has the beta 2 here and log alpha 2 here. This is basically the intercept, and this beta 2 is the slope. So simply have the logarithm of the data and x data, then use it for linear regression of this. Third, we can have a saturation growth rate equation. Saturation growth means it increases, then getting converged like this and going to be stable after a while maybe. And its function is like this. You can see alpha 3 and beta 3 are the coefficients. You can take the inverse of this function, so 1 divided by y, and this function as well, it happens like this. It turns out to be like this, a linearization using inverse. And in here the slope is beta 3 divided by alpha 3, and intercept is 1 divided by alpha 3. Then when you apply the linear regression here, the obtained coefficients will be this and this. Simply from there, this way you can have the linear regression applied to a nonlinear data by converting it using the inverse of the data. So take the inverse of all y's and all x's, then apply the linear regression to be able to get a linear fit. So these are the three common data behaviors, let's say, or relationships that we can convert to a linear data, then apply the linear regression again. But if we have a different data type than the trend of these, maybe in that scenario we are not able to make this conversion, then we need to apply a polynomial, a higher order term polynomial to the data rather than using linear regression. But in this case, we have these three conversions of linearization. The term is called linearization. Then we can have linear data and apply linear regression easily. In this slide, we have an example of a nonlinear data. You can see x's are 1 to 5 and y's are these. So when we only plot the data, it's these values, and they show a nonlinear increase actually. So this kind of an exponential data maybe. When you see this kind of linear increase, you can say that, okay, instead of having a linear regression directed to this, we can try a linearization of this, a conversion of the data to a linear data. And for that, we can use base 10 logarithm, because this looks like a power equation maybe, or exponential as well. You can try both to see which one fits well. So this is kind of a trial and error study actually, or based on your experience on the data behavior, you can decide by yourself. Here base 10 should be fine, and it gives a linear relationship. We need to take the logarithm of x's, which are these, and the logarithms of y's, which are these, and if we plot them, you can see we have actually very linear data, and we can actually fit a line to this data now. For fitting the line, we apply the linear regression with least squares. So simply the data, the linear regression formulation will be this, and we will find alpha 2 and beta 2. And for this, so this is similar to our linear regression formulation. So this beta 2 is alpha a1 and log alpha 2 is a0 basically. And for that we need these x times y values and also x square values. So let's calculate these first. Then we need the summations as well. Let's sum them as well, because the formula that we want to find a1 is this actually, the multiplication of these and summation. So this value 1, 4, 24, n is 5, there are 5 data, minus total x's, which is here logarithms. We have to be careful because we converted the data to logarithms, and total y's here divided by 5 xi's, the square of xi's, this, and the summation of it here. So this xy means a logarithm x and logarithm y actually. So that's why this is logarithm x square, and we need that anyway for this because we converted to logarithm. And this is logarithm x, total logarithm x square, this one. And when we calculate this, it is 175. 175 is a1. a1 means beta 2. So beta 2 is a 175. Then we substitute this to our a0 equation. Mean of y is 0.4282. This is logarithm, by the way. X also mean of the logarithms, these. It's 0.415884 times 1.75. a1 is 1.75. When we calculate this, a0 becomes 0.3 minus 0.3. And a0 is logarithm alpha 2. So we found logarithm alpha 2 here. And when we write these into the equations, basically the equation is logarithm y is equivalent to beta 2, which is 175, logarithm x minus 0.3, because this is logarithm alpha 2 directly. So we can also convert this to a power equation easily. Now actually we fitted a linear equation. This, if you plot this curve or line, you will obtain this. And we will convert this to power equation. Basically, for a power equation, the alpha 2 corresponds to alpha 2 we found here, and also beta 2 corresponds to beta 2 here. So beta 2 is directly 175. We obtained this, but we obtained logarithm alpha 2 here as minus 0.3. So we take the inverse of logarithm to take alpha 2 and write it here. When we do that, anti-algorithm and anti-logarithm actually, alpha 2 becomes 10 to the power minus 03, which becomes 0.5. Then we can write it here. It becomes y equals 0.5, x 175. And we can plot this now over this line, because this is the nonlinear version. And you can plot this curve here and get the nonlinear curve, as you can see here. So this example is a very good example to show how to convert data, have a linear regression, then convert it back to a power equation to have a nonlinear fit as well. Because the linear regression is easy with these calculations, only 2 calculations here, it's better to convert fit than convert back if you want. Linear regression can be implemented as a multiple linear regression as well. We can have more than one input data. Like if you remember, we only have x as input and y's as outputs. We can have x's more than one actually. x1s, x2s, these can be different input variables. And y can be only one again, the output. In that scenario, we will have a linear regression again, but this, for example, 2 variable case, x1, x2. In this case, we will have a plane, a flat plane actually, to fit the data. And it has a1 x1 plus a2 x2 and a0 coefficient as well. So we have 3 coefficients that we need to find. 3 unknowns. Of course, this is the residual. And if you isolate residual, basically it's y minus these, you can see. And again, we use the sum of the squares as the residuals to have the least squares minimization. So we take the square of these by summing them. It is SR. And what we did for the one variable case was, okay, we want to minimize this function now. So we can take the derivative, set it equals 0. So we are differentiating or taking the derivative with respect to each coefficient because these are unknowns. So for with respect to a0, a1, and a2, and set these equals 0. Then express these results in matrix form, as you can see here. Simply, what we did is we have unknowns a0, a1, a2, and just use the coefficients of these as a set of equation format like this. Then we can solve this using a Gaussian elimination technique, for instance, or you can use Cramer's rule as well. You just need to determine these using the data. x1 and x2 data is easy to use, and also y data here, and these are unknowns. You can simply solve this. You can use the MATLAB codes as well to solve this. Let's show the pseudocode for this in the next slide.